Good morning, students. Today we will start new chapter, alternating currents. This chapter is divided into two lectures, and in the first lecture we will cover these topics: alternating EMF and current, average or mean value of alternating EMF and current, root mean square value of alternating EMF and current, AC circuits with resistor, AC circuit with inductor, and AC circuit with capacitor, and the graphical relation between frequency and inductive reactance and frequency and capacitive reactances. The very first topic is alternating EMF. How can we define alternating EMF? Let us see. Alternating EMF is that EMF which continuously changes in magnitude and periodically reverses its direction. That means the EMF is changing continuously, meaning its value is changing with time, and after a certain interval of time it reverses its direction. And the alternating current, in a similar way, it may also be defined as that current which continuously changes in magnitude and periodically reverses its direction. If any electrical component is connected to alternating EMF, the current flowing through that component is definitely alternating current. The alternating current and EMF can be represented graphically as, there is a axis where theta equals to omega t. The values of theta are 0, pi by 2, pi, 3 pi by 2, and so on. And the corresponding time intervals are t by 4, t by 2, and so on. And there is EMF axis or current axis. If we plot a graph, this graph is shown by the blue colored line, and it is graph for alternating EMF. E equals to E naught sine omega t, where E naught is maximum value of EMF. It is also known as peak value of EMF. And if we plot electric current on the same graph, it is shown by the green color line. And when electric EMF is E naught sine omega t, I equals to I naught sine omega t. Let us see if EMF is expressed in terms of cos omega t. Then in that case the graph looks like the second one, and E is E naught cos omega t and I is I naught cos omega t. Remember one thing, in both the graphs electric current and EMF both changes in accordance. That means they are said to be in phase. If current is maximum, EMF is also maximum. If current is 0, EMF is also 0. Or if EMF is maximum in negative direction, current is also maximum in negative direction. It happens only when a pure resistance is connected with the alternating EMF. Now the symbols have their names, as I already mentioned about these things. E and I, these are the instantaneous values of EMF and current. E naught and I naught, these are the peak values of EMF and current. They are also termed as amplitude of EMF and current. Omega is angular frequency, and omega into T is phase, and T is time. Now in a circuit, how can you represent a source of alternating EMF? it is represented by a circle, and within the circle we have a one cycle of sine curve. Now, how can we find average or mean value of alternating current? Actually, if the value of alternating current changes continuously and if it reverses its direction after a certain interval of time, definitely there is a curiosity that what amount of current is actually flowing through the circuit. To find out the effective current in the circuit, we have some mathematical tools by which we may find the values and may conclude that actually what current is flowing in the circuit. And the very first tool or the very first technique is to find average or mean value. And as we know, if it reverses its direction, in first half it will be, if it is positive, in next half it must be negative. To find average, we have to take only first half. Then the average or mean value of alternating current over half cycle is that steady current which will send the same amount of charge in a circuit in the time of half cycle as is sent by the given alternating current in the same circuit in the same time. That it is a kind of comparison. If there is a constant current and for given half cycle, in half cycle, that means time duration of half cycle, if the charge amount due to steady current is same as the charge amount due to a alternating current, then if that charge amount is divided by time, it will give you current. Then the steady value of electric current is equal to the average value of alternating current. Now, as we know, I equals to dq by dt, therefore dq equals to I into dt, where I is instantaneous value of alternating current. Then at place of I, we may write I naught sine omega t into dt. Therefore, dq equals to I naught sine omega t dt. For half cycle, if you want to find total amount of charge, then q equals to integration from 0 to t by 2 I naught sine omega t dt. As I naught is maximum current, it is a constant term. We will take it outside of the integration, and when we integrate sine omega t with respect to time, we will have minus cos omega t divided by t. And when we put the values for omega, we will put 2 pi by t, and after putting the limits, lower limit and upper limit, we will have q equals to 2 I naught by omega, and definitely 2 I naught at the place of omega, it is 2 pi by t, therefore t comes in numerator, and the total amount of charge for half cycle will be I naught into t divided by pi. So the mean value of alternating current I average equals to q upon t by 2, and if we put the values, I average will comes as 2 I naught divided by pi, and it is 0.637 I naught, where I naught is peak value. In other way, you can say the average value of alternating current for half cycle is equal to the 63.7% of maximum current. Now the average or mean value of alternating EMF. By the same mathematics, we may have the same result. EM equals to 2 E naught upon pi, and again it is 0.637 into E naught, or 63.7% of E naught. Now, what is average value for complete cycle? The average or mean value of alternating current or EMF is 0 over a cycle. That is, over a cycle means for a complete cycle, as the positive and negative values get cancelled. That means the current which is flowing in the circuit is not average value, because for a complete cycle the average value will be 0. Then it may be a root mean square or virtual, which is also called effective value of alternating current. The root mean square value, this root mean square term is not new to us. In case of kinetic theory of gases, we have root mean square velocity or root mean square velocity is there. What is the mathematics? This exactly, you can reverse the terms and you may have an idea of root mean square. Get the square of the values, find out its mean, and after getting a square root of that, you will have root mean square value. How can we find exactly root mean square value? And let us see. Root mean square or RMS value of alternating current is that steady current which would produce the same heat in a given resistance in a given time as is produced by the given alternating current in the same resistance in the same time. Again, a kind of comparison with heat produced by constant current and heat produced by alternating current. If these two values are same for a given time, then the value of steady current is equal to the value of root mean square value of alternating current. As we know, heat produced is I square R into T, where I is electric current, R is resistance, and T is time. For a small time interval dt, the heat produced may be given as dH equals to I square into R into dt. At place of I, if we put I naught sine omega t, the expression becomes dH equals to I naught square into R sine square omega t dt. And if you want to find heat produced in complete cycle, we have to integrate the above with respect to time for 0 to t, capital T, that is duration of one time period. Again, I naught square is a constant term. It comes outside of the integration. Resistance of the circuit, again a constant term. It is also outside of the integration. And by solving this integration, you will have I naught square R T by 2. Definitely, after integration, omega is replaced by 2 pi by T, and by placing the lower limits and upper limits, we will have H equals to I naught square RT divided by 2. If IV be the virtual value of alternating current, then the heat produced would be IV square R into T. Comparing these two, you will have I RMS equals to I naught by root 2. If we compare these two expressions of heat produced, RT and RT will cancel out. I naught square by 2 equals to IV square. Therefore, IV equals to square root I naught square by 2. And that comes as I naught by root 2, which is 0.707 I naught. Or in other terms, you can say it is 70.7% of I naught. Now the root mean square or virtual or effective value of alternating EMF, it is E naught by root 2 or 0.707 E naught, and again 70.7% of peak value. Now, mean square value of alternating current or EMF can be calculated over any period of the cycle since it is based on the heat energy produced. The root mean square value can be of alternating current or EMF can be calculated over any period of the cycle. And do not use the above formula if the time interval under the consideration is less than 1 period, because these calculations are for one time period duration. Now the relative values, peak, virtual and mean values of alternating EMF. E average is 0.637 E naught, E RMS is 0.707 E naught. But we have to keep in our mind the given value of the alternating EMF and current are virtual values unless otherwise specified in any numerical problem, or if there is given that such and such value of alternating EMF or current is there, then this value is virtual value. Suppose, for example, 230 volt AC means E RMS is E effective is 230 volt. Now the AC ammeter and AC voltmeters read the RMS values of alternating current and voltage respectively. They are called as hot wire meters because they works on Joule's law of heating. The scale of DC meter is linearly graduated, but the scale of AC meter is not evenly graduated because heat produced is directly proportional to I square. The relationship is exponential one. Now suppose a resistor, pure resistor is connected with a AC EMF. The circuit diagram is shown here. A resistor R is there and it is connected with a AC source. As EMF is E naught sin omega t, I equals to E upon R. Therefore, I is E naught by R sin omega t. Then I equals to I naught sin omega t, where I naught is E naught by R and R equals to E naught divided by I naught. EMF and current are in same phase. As you can see, sin omega t and sin omega t both occurs in E as well as I. Omega t is phase, phase of EMF is omega t, phase of current is omega t. Therefore, they are in same phase. And if we plot the graph for EMF and current, they will like this. The blue color shows EMF and the red color shows alternating current. They are in phase. The peak values are shown E naught and I naught. E is E naught sin omega t and I is I naught sin omega t. Now, if we represent EMF as a rotating vector, then the rotating vectors which represents EMF and alternating currents are known as phasors, and the diagram which shows phasors of electric current and EMF are known as phasor diagrams. Therefore, E naught and I naught both are the phases of E naught represents EMF, I naught represents alternating current. Both are in same phase. Therefore, their phasors are in same alignment. Omega t is the phase. Now suppose if a pure inductor is connected with the AC, inductor is a coil or solenoid. If a solenoid is connected with the AC source as shown in the figure. Again, EMF is E naught sin omega t. Here the law of electromagnetic induction, and as we already discussed in self-inductance, induced EMF in the inductor is equal to minus of L di by dt. And in order to maintain the flow of current, the applied EMF must be equal and opposite to the induced EMF. Or you can say in other ways, the potential difference across the ends of this inductor and EMF induced, the sum of these two must be equal to 0 if it is an ideal inductor. For ideal inductor, the potential difference across it will be 0, as potential difference develops only across a resistor. Or with the help of this also, the EMF is equals to L di by dt in magnitude form. E naught sin omega t will be L di by dt, and definitely di equals to E naught divided by L sin omega t dt. The di is a small electric current. To find total current, we have to integrate it. I equals to integration E naught by L sin omega t dt. Again, it comes as E naught by omega L into cos omega t with minus sign, because integration of sin omega t is minus cos omega t divided by omega. Now the omega is clubbed with L, and I equals to I naught sin omega t minus pi by 2. This minus cos omega t may be written as sin omega t minus pi by 2. Then where I naught equals to E naught by omega L and XL is omega L equals to E naught upon I naught. XL is known as inductive reactance and its SI unit is ohm. Here the current lags behind EMF by pi by 2. Just see, the phase of EMF is omega t while the phase of current is omega t minus pi by 2. That means current is lagging by pi by 2 radian. And if we plot their curves, this is EMF. As you can see, when EMF is 0, current is maximum in negative direction. When EMF becomes maximum, current becomes 0. Then after a time interval of t by 4, they are lagging. The current is lagging behind when t is t by 4, or you can say the phase difference is pi by 2 radian. E is E naught sin omega t and I is I naught sin omega t minus pi by 2. Now we plot a phasor diagram. This is phasor of EMF and this one is phasor of, the red one is phasor of electric current, and you can see here E is in fact I lagging E, or E leading the current I. E is leading, or you can say I is lagging behind. Lagging behind means पीछे रह जाना. तो जब आप इसको रोटेटिंग वेक्टर की तरह लेंगे तो E नॉट आगे की तरफ जाएगा, तो E नॉट और I नॉट के बीच में हमेशा 90 डिग्री का डिफरेंस बना रहेगा, जिसमें I नॉट पीछे रहेगा और E नॉट आगे रहेगा. Therefore the term lagging behind. Now AC circuit with a capacitor. Suppose a pure capacitor is connected with AC source. Then the capacitor connected with AC source. Again the EMF is E0 sin omega t. Definitely Q equal to C into E, as in generally we say Q equal to CV. V at place of V there is E, therefore Q equal to C into E, and it is equals to C E0 sin omega t. The charge is there. If you want to find electric current, differentiate it with respect to time. Then I equals to dq by dt. After differentiation, d by dt of C E0 sin omega t. Ce will be outside of the integration. Then it is d by dt of C E0 sin omega t. Then you can say C E0 will be outside d by dt of sin omega t. The differentiation of sin omega t is cos omega t into omega. Then this becomes C E0 omega cos omega t, which may be written as E0 divided by 1 upon omega c into cos omega t. This 1 upon omega c is 1 upon omega c is XC. 1 upon omega c will be XC, that is capacitive reactance, and its SI unit is ohm. Therefore I may be written as E0 divided by XC into cos omega t, and E0 upon XC is I0. Current leads the EMF by pi by 2 radian. Here current is leading the EMF by pi by 2 radian. Now the graphical representation for electric current and EMF. The blue colored line is EMF and the red color one is electric current. Definitely when EMF is 0, electric current is maximum. That means it is leading. Electric currents lead the EMF. And if you want to draw its phasor diagram, it is like this. This is phase of EMF, blue one is the phase of EMF, then red one I is the phase of electric current. Definitely the alternating current is leading the alternating EMF in case a capacitor is connected to the AC circuit. The difference of phases is pi by 2. Now the variation of XL with frequency, as XL is equals to omega into L. Definitely omega may be written as 2 pi f into L. Then omega is 2 pi f, therefore XL is 2 pi fL, and surely XL is directly proportional to f, that is linear frequency of AC, and the graph looks like this. Now variation of XC with frequency, as we know XC is 1 upon omega c, and by substituting value of omega we have XC equals to 1 upon 2 pi f into c, and here XC is inversely proportional to frequency, and the graph looks like this. There are some important terms. Inductance cannot decrease direct current, it can only decrease alternating current, and capacitance allows AC to flow through it, but it blocks DC. How it blocks DC? For direct current omega is 0, therefore X equals to 1 upon 0, which is undefined. It shows very high resistance towards DC, therefore it blocks DC but it allows AC. This is all about the first lecture presentation, and I hope you will understand with it. And if you have any doubt, you can ask me on my personal WhatsApp number, or you can also ask on Google Classroom. Thank you.